Hello and welcome to my tutorial on how to use this PID tuning tool that I've developed for TVC model rockets. So let's get into it. So this little JavaScript code sandbox can be set up so that you can set up your rocket, put in a bunch of values for your rocket, and you try out different PID values, and you can see how it flies, or sort of how it rotates at least, and you see a bunch of graphs. So, for example, this is a sample output. So if I say tell my rocket to be the initial angle to be 45 degrees, and I want the set point to be at 0 degrees, you can already see it starts this animation here. So if I refresh this again, so if you want to just play a code change again that you made, you just press refresh up here, and there we go. So it goes from 45 over to 0. And there's some vibrations and stuff induced that we'll talk about soon, and then you can see the graph here. So right now the graph is kind of scaled just 5 to -5 degrees, so this is sort of not ideal, but what you can do is you can see here the red line is the sensed rocket angle or the actual rocket angle, depending on how good you set your sensor at, like how accurate your sensor is, which we can talk about in a bit. And then the blue line right now is just showing the integral term of my PID controller. So this is the integral term before I apply a gain to it. Right now I don't have any integral gain, so whoops, actually it's down here. Right now I don't have any integral gain, so it's not really having an effect right now. And you can see the angle goes from 45 way up there, and it gets to 0, and the rocket moves a bit because I have a bunch of noise and a bunch of other things that are trying to affect the rocket and trying to test it to make sure that it's robust in a bunch of noisy and non-ideal scenarios. So let's just talk about this for a little bit. So up here, I'm just importing a plotting library. That can really just be ignored. Just keep that up there. You don't have to modify it. Here are a few variables for position control. So I've been playing around with feeding in cascading PID, like having a cascading PID where you you have two PIDs running. One PID control loop is controlling is basically supposed to control the position of the rocket, and so what it does is it gets the rocket's current horizontal position, and it spits out the angle that the rocket needs to be at. And that's all it does. And we feed that angle that the rocket needs to be at as a set point to the second PID control loop. So that is the set. So basically, the second PID control loop, it takes in the angle that you want of the rocket, right, from the previous control loop, and it takes in the angle that it's at right now, and then it tells you how much to angle the TVC gimbal, like the motor gimbal, to get to that angle. So that second PID control loop, all it does is it says, hey, where do you want the rocket pointing? Okay, I'll figure out how to point the motor in the right direction to get the rocket pointing in that direction. And then the first PID control loop, all that does is says, hey, I need to get to this horizontal value, and I'm at this horizontal value right now, so I'm going to tell the rocket to rotate this much to get there. Okay, so to get this to work, basically you would say control position equals true, and you would give it a set point. So for now, let's say we want I'm going to say the initial rocket angle is going to be 0 for now real quick. And the X set point here is we're going to set it to 10 meters, let's say. And these PID values are, I think, okay for now, but we'll see how it goes. So here, if we scroll down here, you can see an XY plot. So here's a plot of XY, so this is sort of your trajectory of your rocket. So it's started out going to the right towards 10, and then as it gets closer, it starts to slow down, but it still overshoots a bit. And then by the time the thrusters, like the motor burns out, it's still just going to the right. So what we could do is change the thrust. So here we've got a thrust properties sort of section where I can say, well, do I want to use a thrust curve from like a real motor, or do I want to use a constant thrust? So I'm just going to say I don't want to use I don't want to use a thrust curve. I want to use a constant thrust. So we're going to say false, and the constant thrust will be 16 newtons here. So you can see here, there we go. That probably works a bit better. It's a little bit swinging a little bit, but there we go. So now there's our x trajectory here, and as it gets close to 10, it sort of goes, it straightens out. There's a little bit of steady state error, but that looks okay. This graph is a little bit wonky because it's not really used to doing XY plots where it's not really a function. But yeah, you can sort of follow the trajectory upwards this way. Yeah, and then there's also like horizontal values here. So so this is like all your charts, all the values you need for, horizontal x position, acceleration, and velocity, things like that, right? So that's sort of how it looks. Next is vertical values. So this actually, I think is not, this only goes up to 5 seconds right now because I have the sim running for 5. So here's the vertical values. The black line is the actual height, and then the others are acceleration, velocity, and then there's also thrust. So thrust is a constant 16 newtons, so you can see that. You can change the colors yourself in the graphs, as I'll show you later. Here's the thrust, it's just a constant 15 newtons, or 16 here. Here's your TVC angle. So this is kind of interesting. We've got the black line is the commanded, if I zoom in actually, let me zoom in. The black line, can I zoom in a bit more? Okay, that's going to be horrible. But anyways, the black line here shows you what is the, let's say, commanded angle that the PID controller has told the rocket to go to, right? So, or sorry, the TVC, right? So if we zoom into here, you can see there's like a stepped response, right? So there's steps. And that's because we actually have the PID running every 10 milliseconds right now. We can actually change that later in the code, so there's settings for that, so you can change that for yourself. So you have it running every 10 milliseconds and updating. And you can see in the red is the actual angle of the TVC. And you can see it doesn't follow the actual PID angle because servo motors don't go to where you tell them to go to in like an instant, right? Like they take some time to get there. There's some noise, and so this is kind of what's happening. Is let's say something like this, right? So we have this PID command telling us to go down, lower and lower, lower, and then down here, but it takes a while for the actual TVC, I guess, servos to get to that angle. So you can actually specify that delay as well in the code, which I'll show you in the code soon. Yeah, so I've shown you most of the graphs. There's also a graph here on wind torque effect. This is just sort of an experimental thing, so I've been looking into like how to make a more realistic sort of wind gust kind of thing that changes the torque on the rocket to see just how it deals with outside sort of forces. All right, so let's talk about the code a little bit more. So the top part of the code, so the code all the way down to here, let's see, yeah, all the way down to these stars. All this stuff at the top is stuff that you should be specifying, right? So this is a lot of useful stuff that you should specify. Everything after the stars here, it's just simulation stuff. It's things to like set up the canvas to get the rocket to move the way you want it to move, setting up like the height and width of the square of the rectangle of the rocket that's drawn. It's then there's like an initializing PID code, so you can sort of see how the PID code works. There's a different type of PID code that I'm experimenting with that isn't being used. There's also things like limiting TVC angle, so making sure there's a function that makes sure that the TVC angle doesn't go past a certain speed. And there's and then there's like the simulation step. So there's a whole function that actually just does the simulation at each time step, and it calculates the torque on the rocket and also the height and the horizontal distance and all those good values. There's a draw rocket function that just draws this onto the canvas, so that's not really too important to worry about. Then there's the actual simulation and animation steps. That's kind of like boilerplate stuff. Then there's sort of just I'm sort of pushing here. I'm creating like an array just to get the graphs working, and down here are all the graphs, right? So each graph has like a new U-plot kind of thing. So this whole highlighted part is one graph, right? This is the top graph. You can see here we've got a bunch of labels for the graphs, and then for each of those labels we have the data, right? And here we're mapping the time for that data. And then we have the next graph and the next graph, and then that's all we have at the end. So let's take a look back at the properties here. So here you set up your PID gains for the position control loop if you are actually controlling position. But let's say we're not controlling it. We'll just say it's false. Here you set up your set point. So that's where you want the rocket to go horizontally. And here is the range of rocket angles that the PID is allowed to go. So maybe that should be in that section. But this is sort of, if the PID controller, let's say if I say control position equals true, and I want to go to 10 horizontally, you can see how the rocket sort of limits itself to max out at 25 degrees sideways. So it doesn't really know anything about, vertical thrust, like its vertical height, and so we need to tell it sort of like, hey, like you should probably be at, you should limit yourself to a certain angle because this will want to try to get to like 90 degrees horizontally, where you won't get any vertical upwards movement. So I mean, I can set this to 45. And so it's going to go to 45 to get to where it needs to go, and then it sort of it overshoots a bit. But anyways, yeah. So I think we can finish talking about the control position part, because that's not the most. That's just like an add-on. But let's talk about the rest of the properties. So first off is, what angle should your rocket start at? So this is your initial rocket angle. We're saying let's start it at 5 degrees. Let's account for some misalignment in how you aligned your rocket, so it's maybe not pointing straight up at the beginning. There's also a rocket angle set point, so this is where you want it to set, your set point to be at. We want it to stay at 0 degrees, so we'll stay at 0. You can always set it to 45, and it will go from 5 degrees to 45, and it'll try to stay there. But let's just set it to 0. Next is your PID gain. So these are the gains that you're going to be using in your rocket. This is the thing that you're going to be tweaking to get this response the way you want it to be. Next is your TVC to center of mass distance. So this is in meters, and this is just how far away is your TVC gimbal center point to your center of mass of the rocket, because then that's used in the calculation for finding out how much torque that motor is applying to the rocket. Next is the moment of inertia. So this is the moment of inertia of your rocket, or I guess it's mass moment of inertia. But there's a video here on how to measure it, and this one I think is Joe Barnard's video from BPS Space, and I think the time, I put the time at 93, I think, so that gets you to that specific section. My moment of inertia was 0.056 for my current rocket, and I just have it at 0.04 right now, and this is in kilograms, kilogram meters squared. Next is the mass of the rocket. So obviously you need to know how heavy your rocket is to know how high it's going to go. So here it's in kilograms. Next is the max angle range of your TVC. So this is, let's say if your TVC gimbal can only gimbal plus or minus 5 degrees, you put in 5. If it can gimbal plus or minus 7, you put in 7. So this is, I have a function that sort of limits the angle of the TVC to be only plus or minus 5, basically. Next is TVC center error offset. I think this isn't that crazy to like, it's not, I don't think that works really well. If I say it's 1 degree, I don't know if that does much, I think. Yeah, it doesn't seem like, even if I do 10 degrees, Okay, with 10 degrees it kind of is weird, but this is kind of like if you don't center your servos perfectly, you'll have an error offset in the TVC angle. I think what this does is this just sets the initial TVC angle, kind of. It does the same thing. So I actually might just, I'll keep it here and just keep it at 0 for now. Ratio of servo movement to gimbal movement. So this is your servo to gimbal linkage ratio, right? So if your servo motor moves 20 degrees, or let's say your servo moves 20 degrees and your gimbal moves 5 degrees. Well, you have a linkage ratio of 4. This is a ratio for my rocket. And here is your TVC degrees per second max. So how fast does your servo, how fast does the gimbal move in your rocket, right? Mine moves at 60 degrees per second. A good way of trying to measure this is just take a video camera and measure it in slow motion, or you can measure it at normal speed, and you just take the frame that it starts to move at, and then find the frame that it stops moving at, and then you sort of calculate the time that took. And maybe put it a little bit lower than what the actual speed is, maybe, and see how that affects the rocket. Here is the thrust properties. So basically, here, if you want to use a thrust curve, then you can say true here. But if you say false, then the thrust is going to be whatever thrust you put in here that's constant in newtons. The thrust will not turn off in this case, so your rocket will just keep going, infinitely upwards. But this is good to sort of just try out if you don't know what your motor thrust is, or you have an average value. This is kind of good just to try it out and see how the gimbaling works. But if you do set thrust curve equals true, then it's going to use one of these 3. So this one is a C6 Estes thrust curve that I've got from thrustcurve.com, or I don't remember the website name, but from that thrust curve website. And this is just an array of arrays, right? So array of pairs, where the first number is the time in seconds, and the second number is the newtons of thrust. And I have a function that actually interpolates linearly between these values. So even though there's maybe 20 points here, we actually expand those to as many as we need, 1,000 points or whatever. So you'll actually see that right here. So you can see here we have actually thousands of points here for this thrust curve. And so if we go lower, we have the E12 Estes thrust curve, and we have the F15 thrust curve here, which is the one I'm using here. And actually, if you want to select which thrust curve you want to use, like which motor, you can also add your own. So you can go to that website, add your own, or you can just also select, like if I want to use a C6 Estes thrust one, I would just type that in down to here. Okay, so I'm just saying, what is the thrust curve data, and then you just have that array in there. Next is drag coefficient, drag area, and air density. So this is kind of an experimental thing. This is just for calculating the height of your rocket, and it's not really looking at, I don't know if it's looking at just the vertical velocity. I think it's not really caring about side to side, so this isn't very accurate, but the drag coefficient, you figure that out whichever way you want. Drag area and the air density here. And then this is just a function that is up here that you don't have to change. This just is the definition of a function that takes all these values with the velocity, and then it spits out the actual drag force. And so that doesn't really change the rotational torque properties of the rocket. Like this drag will only be applied to a vertical velocity. Or to in a vertical direction. Next is servo delay seconds. So this is how many seconds does it take for you between you commanding your servos to go to a certain angle and that servo actually starting to move, right? Because it takes a while for the servo to actually start moving, and so 30 milliseconds is probably a good sort of safe estimate. Probably a little bit too conservative. 20 milliseconds is probably good as well, but it's really up to you to measure that. A way to measure that is you take an LED, hook it up to your computer, and take a video and have take an LED, hook it up to your flight computer, and have a servo motor as well hooked up, and then basically, in your code, tell the LED to turn on, and right after, tell the servo to go some angle. Take a video of that happening, and then just see how much time it takes between the LED turning on and the servo starting to move, and that is probably a good estimate of your servo delay. Next is your TVC noise amplitude. So, our TVC mounts, or our TVC mounts and the linkages and the holes that the linkages go through can be kind of loose, right? They're a little bit loose fitting, and they're not fully, or they can be loose fitting, and so there's a little bit of slop in there. So this is where you sort of specify the slop for the TVC angle. I don't really know what a good value is here. I hope but that my values are very small, so I put in 0.2 degrees. Something that is like a 1 degree slop is not super great. As you can see, it just really doesn't like that. What this does is this actually is just like noise, so or like it's added to noise. So there's a random number that gets generated that sort of basically, or sorry, not random number. Every time step, a random number is generated and is multiplied by this value, and that number can go from 0 to 1, so your value can, the amount of actual TVC angle that is applied because of that noise can span between 0 and 1 degrees. Hopefully yours is less than that. Next is the PID loop time. So this is how many seconds do you have between each time, like each PID computation, right? So what is your control loop time? So my interval here is 10 milliseconds. And 10 milliseconds seems to work all right. If I do like 40 milliseconds, we can see how that works. Hey, that doesn't look too bad either. 40 milliseconds. I mean, we're not going fast, and we're not we're not rotating at fast rotational velocities at the moment. So, but that's where this would shine. Is if your rocket is rotating at fast rotational velocities, then you would want your loop time to be faster. Next is angle sensor noise. So this is sort of so the PID computation. It actually doesn't look at the actual angle of the rocket. It doesn't because in a real rocket, it's not. You're never going to know the real angle, right? And so in this case, this is kind of adding kind of like a dumb, very naive sort of noise to the angle sensor, and that noise plus the angle is going to be sent to the PID. So we can say the noise is actually 1 degree, and there. So that's sort of what happens. And you can see here actually in this graph, you have a very fuzzy sort of sensed rocket angle. And if we zoom in a bit more, you can see that fuzziness is very noisy, but then there's like a straight line here that you can see, the red line, that is the actual rocket angle. So that's sort of that noise that's added onto it. We can say, the noise of the actual rocket angle is maybe, or the noise is 3 degrees, and so now it's kind of, it's really wonky. So you kind of play around with it. You would basically try to figure out the noise of your sensor and try to put that in here. There's also sensor bias for the angle. If you sort of if you know the biases of your gyroscope beforehand, and you zero out your angle right before launch, then you probably don't need to worry too much about this. You probably don't need to worry too much about this value. You can probably set it to 0, especially for short flights. Then here are like initial values. So here we've got the initial TVC angle is just what the TVC center air offset is. And I'm not sure if this is the best place to put it. I think I would just put this as 0. And this is just the angle that your TVC is initially going to be at. So we can set it to like 5 degrees, and that's just what it's initially at. But hopefully yours, like, you always want it at 0 degrees anyways at the start. There's an initial acceleration, and I don't think there's any use for it because it just happens in the first time step, but then it gets it's just there's nothing added onto the acceleration in the next time step, so it sort of just goes back to normal. So that doesn't change anything. Then there's an initial velocity, which does make a difference. So if I say 0.1 radians per second, the rocket, or let's say 0.3, you can sort of see the rocket spinning the other way. That's still a little bit weak. Let's see another one. There we go. So it's kind of, if I do 1 radian per second, you can see it wants to rotate to the left. If I do 2, there we go. See, so it's having a little bit of trouble rotating it back to where it needs to be. Here it's way too much, so it needs to get back. And then by the time it gets back, it runs out of thrust. There we go. Okay, so there we go. Initial velocity. We can say that's 0. You can add like a little bit to test it out. This is kind of a good thing to try out and to see if your PID values, your gains are robust. Another one is torque noise amplitude. So this is just a very crude way of adding some noise to the torque that's imparted on the rocket. And so this probably will be a bit much. No, it's not bad. We put 2. This will be a lot. But the problem with this one is that this happens every this kind of torque noise happens every time step, and it's random every time step. So if it's if this noise is Gaussian, then it will, or if it's like even, you know, it's the same amount of I guess there's the same chance that it'll be above 1 as the same chance it'll be below 0. Or sorry, the same chance it'll be above 0 is the same chance it'll be below 0. And so it sort of balances out a lot. So you could probably set this to 0, but there's another value here that's the constant torque bias. So this is what you'll have, like a constant torque happening. And so you can try out, you know, 0.1 here, see what that does, and we refresh again. And so that constant torque is wanting to rotate that to the right, and then when the thrust runs out, that constant torque is constantly adding more torque. So this is kind of a good one to sort of test out. And here we have 0.5 Newton meters. There we go. So we have that constant torque pushing it the other way, and then all right. And here's a another section here that's sort of used to calculate wind torque, but not sort of constant, you know. So this is actually that curve, that wind torque effect curve that I've shown you. So what happens is here we say what is the amplitude, so that many Newton meters. So let's say, you know, 0.05, and the frequency we can say, okay, let's say half a hertz, and we can say, okay, so you can sort of see now the torque, that wind torque is pushing it left, right. I'm going to make this a 0 again. So that wind torque is pushing it left and right here. So yeah, there we go. That's the wind torque. And you can sort of see how that wind torque, so it goes up and down and up and down. And you can set this to be different frequencies just to get the, let's say, response that you want. So here's another one. Here's just goes up and down. We can do 0.05 as a frequency, and then that'll just be, the torque will go slowly upwards. And yeah, so you can test those out. That's another good thing to test out to make sure your gains are working all right. Here is the lastly, yeah, here are the settings for the simulation. So it's just how long do you want to simulate for? So 5 seconds. I mean, usually you simulate for maybe a second or two more than your thrust curve. Yeah, a second or two more than your thrust curve. If you want to see how high, how high your rocket will go, so like a trajectory, you probably want to simulate for longer because you want to give some time for that rocket to fall. So if we do 15 seconds here, refresh that, and then we go here, and there we go. So now we can see how high it goes, and we see the whole trajectory here, and it goes down. Okay. And yeah, and then obviously it's going to be spinning a lot because there's like wind torques and things that sort of aren't 0 still, and it's just going to keep spinning and stuff. But that's fine. Lastly is your delta t seconds. So this is just how long is the time step for the simulation. this value here, 0.0001, is good. The lower these values, the more, like, let's say, accurate the simulation is, but also if you add another 0 here, it'll take 10 times as many points to create that simulation and 10 times as many loops to sort of do that. So it does slow things down. 0.001 is pretty good, and that works as well. But you can sort of see, so let's say we go with 0.001. Oops. Yeah, let's say we go with 0.001, and we run the simulation, and it runs faster, or it completes faster, and we'll see, okay, like, what is the vertical values that it's gone up to, right? So the highest height is maybe about 60.405 or so, right? If I go 0.001, then the highest height is maybe 60.7, 60.7. So it's not a big change, maybe, half a meter in vertical height over a whole flight. So it's not a huge change, but if your computer can handle it, 0.001 is a good amount. Right now it's not using the trapezoid rule, so Runge-Kutta, to integrate. It's just using like a regular, I guess, rectangle rule. Feel free to modify the simulation where you see the rectangle rule to the modify to the Runge-Kutta way, and that will make it more accurate, but also and probably let you lower the delta t value as well, so it'll be faster. Yeah, and here let's just really quickly go into the PIDs. So this is where I initialize the PIDs. So the way it works is there's a function up here, this one, init PNID, and it actually returns a function. So it's like a JavaScript thing, I guess, but this probably happens in other programming languages as well. But this function returns a function. So what happens is when you call the init PNID function, you're actually going to get another function. So you're going to actually get you're going to get an object. So you're going to get an object that has access to the proportional errors, the derivative errors, and the integral terms, or the integral errors. And you also get that object also has access to the compute function, which actually does the modifying, right? So this is kind of like setting up a class, I guess, right? Yeah, I guess this is like setting up a class. What we're going to do, so what we do at the bottom here is to use it, we just say, okay, well, our TVC PNID is going to init the PID, and it's going to put in these gains, and then it's going to put in our angle range for the servos, or for the gimbals. That might not be the best name for it. And then we also have a PID here, that's a position PID, which takes in the gains for the position, and we give it a rocket angle range. And then in the simulation function here, we basically check if we're controlling the position here, and if we are, then we're going to grab a angle that we need from the X position PNID, and then we're going to basically put that angle into, right here, we're going to put that angle into the PNID with the previous rocket angle, and that TVC PID will give us the command that we need. If we have control position equals false, here we do this else here, and we're basically only controlling the TVC PNID to the set point. So that'll be the just the rotational set point. Then there's a bunch of things, just sort of like steps that we're waiting. This one actually we can just say that's off. But we can actually, this is an interesting thing. So you can actually tell the set point to be something else at a certain amount of time. So I can say, well, if I times delta t seconds is maybe 1 second, I can say, well, I want a set point of 20 degrees. And let's see what that does. So here we go. And there we go. So it went to 0. Let's say it's at 1.5. So we say it went, so we'll see it goes to 0 at the beginning, but then at the 1.5 it goes to 20 degrees. So that's another kind of cool thing to just sort of try out if you want to do like a downrange sort of rotation maneuver. So I just leave this in and set it at 0. Actually, I probably shouldn't. I'll just comment this out, and then if anyone wants to use it, you can use that. Here is just a sort of thing that is calculating whether we can or put in the new like PID, like actually do the new PID. Or sorry, this is calculating whether we can change the rotation of the servo yet. So we say, okay, if it's more than the steps that we have to wait between the PID commands, we're going to grab the TVC angle that we need, or that we can use, based on the commands that we put in and the angle before, and then we basically say, well, the new angle, we're going to add that. We're going to also add things like noise to it, and then we're going to say, okay, well, the thrust is the thrust at that time, and then multiplied by math.sine times that angle and stuff. Else, if it hasn't gone over that step, then we basically are not limiting that TVC angle anymore, I think. This part kind of, sort of forget what this is doing. Next is the, it's just like here's a torque calculation. There's certain things over here like that are some conditionals. So this is, I think, the last thing maybe I'll talk about, I think the last thing I'll talk about is the conditionals. So there's certain conditionals that are occurring because the simulation doesn't really know whether to rotate or when to turn on the TVC or off, right? So it doesn't know when to turn on or off the TVC. It doesn't know when we can actually tell the say that the rocket is going horizontally based on the height, right? So, for example, if your rocket is on the ground, for a while, that rocket will not be lifting up off the ground, right? Like you have a thrust. So actually, we can see that, I think, happening here. If I zoom in, we have a thrust here at 2.5 newtons, but we have a velocity of 0, we have an acceleration of 0, and we have a height of 0. So this rocket is not experiencing any of those things right now because that thrust has not been sufficient enough to lift it up. As the thrust increases, then we start getting a velocity. So here, or actually this is where we start getting an acceleration. So the red is the acceleration, so the acceleration accelerates now, and we start getting a velocity, and we are getting a height, but right now it's super tiny, that it's 0.0000, and we don't have any more decimals that are showing right now. But as we get closer, we get a height that's going up and up and up and up, and then there's a height, right? So the same thing happens with the vertical parts, so the horizontal. So if we zoom into the horizontal, until the rocket height is anything more than 0, we're not going to move left and right. Just because the ground is, let's say, we're saying that the ground is imparting a friction. This doesn't really take into account times where your rocket might be on slippery, wet grass, and it actually doesn't come off the grass, but it still goes sideways. This is just to make sure that we're not considering it actually leaving the pad until it actually vertically leaves the pad. And yeah, so this is sort of where it happens, right? So there's that acceleration, and that might not be the right value we should use for it. This should probably be something less. But I think actually that is accurate. Anyways, yeah, and I think that's really all that I have to explain. So I hope that you enjoyed, or that you can find use from this tool, and let me know of any mistakes or any issues that you see with it, or any improvements that you think I can make to it to make it more realistic and help out. Yeah, so thanks for watching, and I hope if you have a real rocket that you're going to be launching, and you use these PID values to test it, and you've actually launched it with those PID values, and you have footage and data, let me know. Send me that data. Send me that footage. I want to see if I want to see how well your real rockets do compared to this model, and see how well this model sort of simulates these things. Because that's always cool to see that your simulation is very close to the real thing. That's really awesome. So it really validates things. So and it also helps me fix things, right? So yeah. Anyways, thanks for watching, and yeah, I'll maybe make another video sometime on like how the math works or anything. But yeah. Anyways, cheers.